Now in this video we're going to dive into ranking the power of hydrogen, which is also known as increase in the pH, and in this particular part we're going to rank the following in order of increase in acid strength and also explaining the reason why that is the case. We're going to focus now on this particular compounds, which are 5 in total, and also being able to look at these compounds you need to be able to identify and also categorize various compounds based on various definition of acids and base. Now looking at this particular part, we notice that we have hydroxides present, which you categorize as bases, and you see hydrogen positioned right here and another hydrogen positioned right here, which are categorized to be acid. And we know from various experiences that ammonia, which is NH3, is considered to be a weak base. And since we have that, the next step is to first let's look at the metals attached to the hydroxides, and we notice here that we have rubidium hydroxide versus that of calcium hydroxide, and comparing these two we need to see which one is a stronger base. And to notice which one is a stronger base, we have to look at the metal ion. First, let's look at what are the variables that actually influence this particular strength of the base. First, we're going to look at the atomic radii, and the atomic radius is actually known to be the distance between the center of an atom here, which contains protons and neutrons, but that force of attraction is actually influenced by the protons in the nucleus and the outer part of the particular atom. So this distance here is called the atomic radii, and by comparing and also looking at the periodic table, we notice that rubidium is actually in group 1, however calcium is in group 2, and also the period of rubidium is noticed to be in period 5, and for calcium in period 4. So looking at the atomic radii, there are various variables that actually influence the atomic radius. First, the Z effective nuclear charge, and the Z effective nuclear charge actually describes the magnitude of the nuclear force of attraction between the protons which are positioned in the nucleus and that of the outer electrons which are actually positioned right there. So in that case, the more core electrons that are actually between the protons and the outer electrons, the weaker the force of attraction between the proton that is inside the nucleus here and the outer electrons right there. So that is one particular variable that influences the atomic radius. Now the next one here is the lattice energy, which is the energy released when dissociation happens. Now the two ions that are present in this particular base is a metal and hydroxides on both particular compounds, and what we notice is that if you lower the lattice energy, that results in a specific lowering of the Z effective nuclear charge from the metal ion, which results in easier dissociation. So we need to be able to take note of the lattice energy. And finally, charge density, and the charge density is actually a combination of the charge, yes, and the volume of that particular metal. So let's dive into rubidium versus that of calcium and which one is a stronger base based on that. Now the atomic radius actually shows that it actually has 52 picometers versus that of calcium, which has about 100. And then looking at that of the Z effective nuclear charge, we notice that rubidium has 9 versus that of calcium, which has plus 10. And also if you're looking at the lattice energy, the lattice energy we notice is actually dependent on when rubidium shows a smaller charge density, which is based on the combination of our charge, where rubidium has a charge of plus 1 versus that of calcium, which has a charge of plus 2. However, looking at the Z effective nuclear charge, we know that if you increase the Z effective nuclear charge, you automatically generate a smaller atomic radius, which is also pretty much equivalent to the volume of that particular electron cloud. So therefore, rubidium will have a smaller volume compared to calcium, which has a larger volume. So if rubidium has a larger volume compared to the charge, calcium will have a higher charge density. However, as the denominator becomes smaller for rubidium, the charge density becomes smaller. So in this particular case, what happens to the lattice energy is that the energy released in rubidium hydroxide will be lower than that of calcium, because of the fact that rubidium shows a smaller charge density caused by the Z effective nuclear charge to be smaller than that of calcium. So as a result, rubidium will have a higher pH because the dissociation will be greater than that of calcium hydroxide, based on the dissociation of rubidium hydroxide to form hydroxide ion, which is released quicker than calcium, which is a little bit slower in that process of dissociation. Now that's out of the way, we'll actually be able to categorize first rubidium to be the strongest base, hydroxide, then followed by calcium hydroxide, and we know that ammonia in this case is a weak base, so it's somewhere in the middle. Now the final one is to be able to investigate these two, which is as follows. First, we actually have hydroiodic acid right there versus that of hypobromous acid. So once we have those two, we'll be able to first draw the Lewis structure, which is as follows. We have iodide with lone pairs and is attached to hydrogen. However, we have the hydrogen here attached to oxygen, which has 2 lone pairs, and this is attached to bromide, which has 3 lone pairs. So by comparing the Lewis structure and also noticing first that iodine is actually a group 17 atom versus that of oxygen, which is in group 16, and also looking at the period, which is period 5 versus that of 2, we actually notice that the size of iodide is way bigger than that of oxygen. So once the size is bigger, and also looking at the electronegativity of iodine, which is 2.5 versus that of oxygen, which is 3.5. One other condition we need to take note of is the inductive effect on the hydrogen. The inductive effect on the hydrogen in hydroiodic acid actually shows that since the size of iodine is bigger, here we have a poor orbital overlap with that of the hydrogen atom right here. So as a result of that, the inductive effect is way stronger going towards this particular iodide right here, making the bond weaker versus that of oxygen, which has a smaller size, generating a better orbital overlap with the hydrogen and the stronger bond, resulting in a smaller inductive effect right there. So as a result, this bond pair right here between the hydrogen and the iodine will actually be weaker, resulting in water to come in and easily pick up the hydrogen based on the Lewis acid concept to form a stronger acid here compared to this other compound right here. So as a result, our conclusion is that this particular compound is a weaker acid than hydroiodic acid. So this is the ranking and the rationale behind this particular investigation right here. And please hit the comment down below. Let me hear your thought about other variables that can contribute to the acidity of a specific compound. All the same, stay smart and believe in yourselves.